Okay, hi everybody, welcome to this week's Geo tutorial. I'm joined this week by Professor Zoe Robinson from Keele University. Zoe's going to be speaking about tackling the climate emergency, carbon, climate, ecological and energy systems. Just as I always say each week, feel free to go back and review this stream at a later date if you wish to. I will upload the PowerPoint from this lecture shortly after we finished, so feel free to go back and download that and just go through that at your leisure. You can check out all the upcoming lectures and tutorials we've got on the Geo website in the live events section, and any past events you can find in the past events section. If you do have any comments or questions, please feel free to leave those in the chat on the right hand side, and we'll get to those at the end. All right, so I'll hand over to Zoe. Thank you.
Thank you very much, Aaron, and thank you all for tuning in to this session. So it's a very broad-ranging topic we've got. So tackling the climate emergency, and in doing that, thinking about our carbon systems, the climate system, as well as ecological and energy systems. So an awful lot to get through in the next 50 minutes or so. So I think we've heard enough about me. I work at Keele as a professor in sustainability stuff. In terms of this talk, what we're going to be looking at is two main sections. The first is focusing on, well, what's the emergency? We started off with a title about the climate emergency. Well, what is the emergency? So we're going to have a look at trends. We're going to have a look at sort of the global nature of warming, something about terminology, look at the carbon cycle, look at human versus natural forcing and climate change impacts. Then we're going to go on to look at solutions. And that's going to cover looking a bit at political will, political systems, energy system solutions and nature-based solutions, and with a really quick nod to thinking about other solutions. And then we'll wrap up and see what we've covered in the previous sort of 50 minutes or so. So the first sort of thing I want us to focus on then is really thinking about, you know, what's the emergency? Why is it an emergency? And exactly sort of what do we mean by that? So you're probably familiar with maybe sort of images like this that we've had in the media since really sort of 2018. And these sort of statements and headlines around having 12 years to save the earth, 12 years to solve climate change. But we need to really understand, well, what is the science behind these statements? You'll have also seen headlines like this. So, you know, talking about just the real sort of severe nature of climate change, the fact that, you know, almost year after year, we seem to have some of the hottest years on record. But again, we need to unpack some of the science to really understand what's behind these headlines, and in doing that, really try and understand what are our potential real solutions. So I've got a few graphs for you. There's an awful lot going on in this image here, but what we can see is down at the bottom you have a bar that says total net anthropogenic, and that is talking about so anthropogenic, we mean human caused, and it's whether we have forcing of climate in a sort of a positive warming, which is where it's right hand of that zero marker, or forcing of climate to cause cooling, which would be left hand of that marker. And then each of these rows down this graph represent a different forcing factor of climate. So there are lots of different things that affect climate or that affect global temperatures. And some of those, the ones at the top in red, so things we'll be familiar with, our long-lived greenhouse gases, they all cause warming to different degrees. Below that, we have some things which can also cause cooling of climate. But you'll see if you go further down, if you add all of those up, that overall, all of these factors, we combine it all, cause warming. We also can see that the far right-hand column, LOSU, stands for level of scientific understanding. So what we can see is those first couple of rows of our long-lived greenhouse gases, we have high levels of scientific understanding. So we know that they cause warming, they force the climate in a warming direction, and we have a high level of scientific understanding about that. And what I'm going to really focus on throughout this session is more about those greenhouse gases around and about the carbon cycle. So the next graph for you, don't worry, it's not all about graphs at all, but inevitably if we talk about climate, then there's going to be some in there. If we look at this graph, we can see that we have, it's basically showing us our global temperature increase, and the 0 mark is the baseline of the period between 1850 to 1900. So it's showing us sort of warming above that baseline. And what is really clear is that warming trend there. As we look at, we've either got an orange line showing all externally forced temperature change, or just the yellow line, which is just the human induced temperature change. And you can see a pretty close sort of those two lines follow pretty closely to each other. So we see there, this trend as a global average figure in terms of temperature increase. But that leads me on to another important question, which is, well, what do we actually mean by global warming? So we often hear these sort of single figures bandied around. So for example, since the Industrial Revolution, we've had round about 1 degree C of warming. But what does that really mean in terms of one single global figure? Because if we look at a map of the world, we see that some places have warmed more than others. So in this graph here, the darker the colour red, the more warming has occurred at the surface. And this is between 1979 and 2005. But where we have blue, we have some cooling. And so this warming across the globe isn't homogeneous. It's not the same amount everywhere. So again, where does that global warming single figure come from? Well, it comes from measurements of warming, measurements of temperature change across all of the globe. And here on the right, you can see that we've got a picture. It's the globe split up into sort of grid squares. And you can imagine putting all of our observations of temperature change in those different grid squares. And the grid squares are different sizes. So we then average all of those measurements in those different grid squares according to the size of those grid squares. And that kind of gives us that single global average figure of warming. The pictures on the bottom are just to highlight where our temperature records come from. So some in the middle there, land-based measurements, some sea surface temperature measurements from the past, but now really good global coverage through satellite imagery. So sometimes it's just worth us stepping back and thinking about, well, what do we mean by those sort of a single figure? What's hidden behind it? Okay, and so we've looked then at temperature change. We've looked at a globe, what that might mean in terms of a global figure and the spatial variation behind that. And we saw from that first graph that our greenhouse gas emissions, so greenhouse gases, are a really key contributor to this warming trend. And this is a really classic diagram that you might well be familiar with, but you can't talk about climate without showing this diagram. So it shows us carbon dioxide concentrations in the atmosphere since late 1950s. And it shows us that year on year, the amount of carbon dioxide in the atmosphere is increasing. And I've been lecturing, teaching, educating about climate change for 16 years now. And it's really quite remarkable how much I've had to change my teaching slides because of the amount of carbon dioxide in the atmosphere is going up every year. The other thing to draw attention to on this slide is this sort of sawtoothed pattern. And that is representing a seasonal variation in carbon dioxide in the atmosphere. And basically, carbon dioxide levels in the atmosphere are lower in the summer because, or in the northern hemisphere summer, and that's because we have more photosynthesis going on, removing carbon dioxide from the atmosphere. And I just love the fact that we can see the effect of plants photosynthesizing in those global records of carbon dioxide. And then there's another important graph that we need to cover, and that is actually looking at our emissions of carbon dioxide. So what are we actually producing and emitting into the atmosphere? And so the grey line on this diagram is showing emissions from fossil fuels, from cement, and from flaring of gas. The sort of oddly horrible brown colour is associated with emissions from forestry and changes in land use. So we can see, 1950, where this rate of increase in emissions from fossil fuels just, really increases. And we can see that on the right as well in this graph. So that the bar on the left shows us total emissions between 1750 and 1970. And the bar on the right shows total emissions between 1750 and 2011. And it shows just how much that there has been in terms of emissions over really a relatively few decades. So there we have some of the key trends which really sort of underpin what we need to talk about and understand around why we are talking about a climate emergency. Before I go any further, I just want to say a quick note about terminology that we might use in this field, and whether we're talking about carbon, whether we're talking about carbon dioxide or carbon dioxide equivalent. So what we can see, I suppose, from the graph, it's showing us all of our global greenhouse gas emissions by gas, and by far and away that the greatest in terms of the amount is carbon dioxide, mostly from fossil fuels, but also from forestry and other land use. But we also have those other greenhouse gases as well. So why do I say that this is important? Well, sometimes you might hear people talk about carbon dioxide equivalent. And carbon dioxide equivalent, which is usually framed as CO2e, is all greenhouse gases reported in terms of the warming potential of carbon dioxide. So we're only using one value, we're calling it carbon dioxide equivalent, but it actually involves all of our greenhouse gases. So sometimes people say carbon dioxide when they actually mean carbon dioxide equivalent because it includes all of the greenhouse gases. But equally, some people say carbon when they're actually meaning carbon dioxide, or they say carbon when they're meaning carbon dioxide equivalent. So I just want to flag up that it's important that these things are different, but you will hear them being used interchangeably. And to be honest, as I talk through this session, I will probably talk about carbon, but really I'm meaning carbon dioxide equivalent. But it's worth knowing what might be behind the terms, and also being really careful about our language. I'll try to be good, and also, you know, what might be what language other people might be using. Okay, so the next thing that I want to look at is the carbon cycle. And please note, when I talk about carbon, I mean carbon here, and carbon exists in many different forms in every part of the natural system, and it cycles between different stores within the natural system. And these cycles can be at different rates. So there's some carbon which will move very slowly from one store to another store. And then there's other parts of the carbon system where carbon moves very quickly between different stores. And so, as geographers, we're really good at thinking about systems and how different things interact within a system. And thinking about sort of the carbon system or the carbon cycle is a really sort of key part of how our understanding of as geographers can help us understand both the problems of climate change and maybe also the solutions as well. So if we just briefly look at this this diagram here and what it's showing. So there's three different colors being used. The yellow is showing us our natural fluxes. So that's really important, you know, that carbon is something which exists naturally in the environment, and it moves naturally between these different stores. So the yellow shows us our natural fluxes or our natural flows. The red writing shows us that the human contributions, the human sort of changes within the carbon cycle. And the white figures are the amount of carbon stored in different areas. So in terms of the units, also very important for us to talk about, we're talking about gigatons per year, so billions of tons. Okay, so we have, you know, significant storage within soil. We've got significant storage of our fossil carbon, think fossil fuels, because that's our stored carbon there. We've got stored carbon in the deep oceans and in sediments in the oceans. We've got carbon stored in plant biomass, in the surface of the ocean, and in the atmosphere as well. And we'll see exchanges of carbon between the atmosphere and the ocean, in both directions and within the ocean as well. And then we see cycling of carbon from the atmosphere through our biomass and plants into our soil, but also being produced by our soil and by our plants as well. Now, in terms of the human interventions, this is where we are changing the rate within the system. So we're changing the rate at which this fossil carbon is released by burning it, you know, really, really rapidly releasing it into the atmosphere. And that also has an impact in terms of, actually, it increases the carbon being taken up by photosynthesis, because actually plants, they love carbon. And so some plants will be photosynthesizing better as a result of increased carbon dioxide in the atmosphere. And we also see an increase in the carbon dioxide going into the oceans. And that is having an impact on a related environmental issue called ocean acidification, where ocean water is becoming more acid. And that's because if you take the gas carbon dioxide and you mix it with water, you basically get carbonic acid forming. And so that's sort of seeing how we get ocean acidification occurring. So we need to understand our carbon cycle and that sort of system of cycling of carbon and how humans have influenced this cycle. Okay, so when talking about climate change, which I've done for many years, sometimes you can still come across people sort of saying, well, doesn't climate, isn't it, it's natural. And, climate has always changed. Climate does change due to natural processes. However, we know that the change in global temperature that we are seeing now can only be explained by reference to the carbon dioxide and other greenhouse gas emissions that humans are releasing into the atmosphere through burning of fossil fuels and through some changes in land use. Now, depending on how big your screen is will depend on how much of these graphs you can see. The critical thing to get across is that there is, in all of the graphs, there is a black line, and the black line is showing observations. So if it's a graph about temperature, which most of them are, the black line is showing observed, measured temperature. And then the pink sort of shading and the blue shading, they are the results of computer models. So where climate modelers take all of the information that we have about the climate system, we create computer models, we run those computer models. And it's only where we have computer models which include human factors that those computer models match the observed temperature changes that we see. Whereas if we run a computer model which just looks at natural forcing factors, natural factors which affect climate, that gives us that blue shading, and we see that actually that is a long way off from our observed temperatures. So we see, we can only, our really detailed climate modeling shows us we can only recreate in our computer models the temperatures we observe if we include the impacts of human activity and the release of carbon dioxide and other greenhouse gases into the atmosphere. Okay, so this is covering some of the background sort of science. But it comes back to then what our first question, well, that's all very well, yeah, understanding that science, but why the emergency? Why now talk about a climate emergency? And that comes down to a phrase called carbon budgets. And this is basically the estimated amount of carbon dioxide equivalent that the world can emit while still having a chance, of staying below a warming threshold, for example, 1.5 degrees C. And bear in mind, we've already reached about 1 degrees C above pre-industrial times. And we now kind of realise that we would really like to keep global temperature increase to below 1.5 degrees C. And coming back to the carbon budget, so carbon dioxide stays in the atmosphere for a long time. So everything that we emit, it stays on average in the atmosphere for maybe 100 years. Now, bear in mind, it is being removed by different processes, but on average, it stays in the atmosphere for a long time. So as we continue to emit carbon dioxide day by day, year by year, it accumulates in the atmosphere. And we've also now worked out how much carbon dioxide in the atmosphere is likely to contribute to a particular temperature increase. And we also know how much we are emitting year on year. And so really by sort of looking at how much carbon in the atmosphere will lead to an amount of warming that we want to stay below, how much we're emitting year by year, we can work out how many years of emitting that amount of carbon how many years we can carry on doing that before we filled up our carbon budget and we'll have that degree of warming. So I hope that sort of makes sense. Back in 2018 now, there was a really influential report which was published by the Intergovernmental Panel for Climate Change, which is a big sort of international body of scientists who bring all of the science together, and it's the sort of our best understanding of the science. They published a report in October 2018. It was a special report on global warming of 1.5 degrees C, and in it they basically said we've looked at the impacts of global warming of 2 degrees and above. We've looked at the impacts of 1.5 degrees, and we really need to keep global warming below 1.5 degrees. And they said, based on current emissions, we have 12 years left before we effectively blow this budget. And so that changed everything. It changed the way that climate change was being talked about. It changed people's language from just talking about climate change to talking about a climate emergency, highlighting the urgent need for action. Okay, so hopefully that's addressed that first question about why an emergency. What I want to look at now is probably, well, we've looked at some of the urgency, but I just want to have a little focus in terms of some of the impacts. So again, depends how big your screen is as to how much detail you can see on this figure. But if we can imagine each of these vertical bars is a different climate-related impact. And it ranges from impacts on warm water corals, mangroves, fisheries, the Arctic region, terrestrial ecosystems, coastal flooding, fluvial flooding, crop yields, tourism, and heat-related deaths, basically. And then we can see these faint horizontal bars, and at the bottom it says 0, so that's sort of no warming. And then the grey bar kind of gives us around about 1 degree warming. Then sort of the second line up gives us 1.5 degree warming, and the highest line is 2 degrees warming. And what this sort of shows is the severity of the potential impacts at these different amounts of warming for these different things which are going to be impacted. So if we look at this first bar, which is looking at warm water corals, basically when we get to purple means we have a very high risk of severe impacts, which are likely irreversible. And we see for corals, we are pretty much already at that stage at 1 degree, and we are very purple at 2 degrees. If we look at maybe the Arctic region, 4 bars over, we see by 2 degrees, we're into that purple, very high risk of severe impacts in the Arctic. Whereas at 1.5 degrees, we just have severe and widespread impacts and risks. So this is from this special report on global warming of 1.5 degrees C. And in summary, it says impacts at 2 degrees C of warming are much worse than they are at 1.5 degrees C, and therefore we should really try and keep warming to below 1.5 degrees Celsius. And if I just take a quick journey through some of the impacts that we've already seen. So at the top, our lovely penguin, I think that's a Adelie penguin. We've seen colonies in West Antarctic decline by 80% since the 1970s. We've got a seal here on the right. In Svalbard, I can't remember these seals. In Svalbard, there was almost no pups born in 2006 and 2007, which was the first time that the fjords didn't freeze in recorded history. Bottom right, we see corals, staghorn corals here. We have already seen a 98% decline in parts of the Caribbean since 1980. And we see turtles being affected by temperature rises. Warmer sand means more females are being born, but changes in ocean temperature are also affecting the distribution of their prey, and they also feed around corals as well. So these are impacts we've already seen. If we look at the human environment, we are already seeing significant flooding, maybe from storm surges associated with rises in sea level, making these instances worse. We've seen wildfires in Australia, in the US, wildfires which are worse than were predicted by climate modelers for this stage. We've seen record-breaking temperatures in France, which have killed 1,500 people in a single heat wave. And these heat waves are 5 times more likely with global warming. And we see increasing intensity of damaging hurricanes as well. So, these are the impacts which are being seen at 1 degree C increase in global average temperature, which gives us an idea of just why we need to ensure that we really try and limit the global temperature increase. Okay, hopefully now, let's take a pause. We've covered, why this is an emergency. This is something that we need to act on. We are seeing sort of severe impacts and how those have accelerated over the last few years as well as the last few decades. But now, let's think about solutions. And there are solutions, and there are some really positive messages as well that we can take away. So don't sort of walk away from this sort of in despair. So let's talk about some solutions. So the first thing I want to talk about is sort of the political sort of will that we are now seeing. Back in 2015, you might have heard reference to the Paris Agreement. This was a landmark sort of moment of international governments coming together to say, to really sort of put a mark in the sand about tackling climate change. And the 2015 Paris Agreement, this is an extract from the agreement which says it's about to take action to hold the increase in global average temperature to well below 2 degrees C above pre-industrial levels and pursue efforts to limit the temperature increase to 1.5 degrees C. This is what led to the further work into looking at the science behind the difference in impacts between 2 degrees and 1.5 degrees. And now we're pretty sure that 1.5 degree is what we should be targeting. But they also went on to say that these reductions should be done in accordance with best science and absolutely critically on the basis of equity between countries as well. Now, that's a sort of an international picture. Just to look at a quick sort of UK picture. The UK has been seen as very much a leader in climate change legislation, with the Climate Change Act in 2008, which put in law the requirement for the government to reduce greenhouse gas emissions. In 2008, the requirement was to reduce by 2050 emissions by 80%. However, in the back of this special report of 1.5 degrees C, the further work has been done, and the report in the middle is a report from the Committee on Climate Change, which advises the UK government on its pathway to carbon reduction. And they produced this report, called Net Zero, the UK's contribution to stopping global warming. And in that report, they stated that it was feasible and desirable to aim for net zero emissions. And that basically means that we need to reduce all of our emissions, and what emissions we can't reduce, we need to remove or offset in another way. And that report led, when Theresa May was Prime Minister, to the UK government changing its legally binding commitment from an 80% reduction in greenhouse gas emissions to net zero by 2050. And this is really important because it means that, having made a commitment to get to this phrase of net zero carbon emissions, there is no place for any industry to hide. Every industry, every business must tackle their greenhouse gas emissions, because that is what is going to be required by law. It's what the government is legally committed to. So that sort of political sort of landscape is important. The fact that no industry now has anywhere to hide means that we're seeing really interesting and exciting innovation around a low carbon or a zero carbon future. Now, this is also being tackled at the organisational scale. So I just referenced my own organisation where I work, Keele University. So we were one of the first universities to declare a climate emergency back in May 2019. And to say we had a commitment to reducing our emissions to net zero by 2030. Now, that's really ambitious. We're still working on the action plan to get there, but we've outlined now a set of principles to help us develop that final action plan. And these principles are around producing our own renewable energy, reducing our carbon dioxide equivalent emissions, but also removing emissions using our campus as well. I think this is a useful way to sort of think about it. So we don't just go down the road of thinking just about renewable energy and producing renewable energy. We've also got to reduce our emissions through energy efficiency and thinking about the emissions associated with everything we do. We also need to remove our emissions by thinking about the natural environment, which I'll come to. The thing I want to focus most on, start with, is energy sustainability. Now, energy is the cause of the majority of our emissions. But when we talk about energy, I'm talking about industry, I'm talking about buildings, I'm talking about transport, all of those different areas where fossil fuels are burnt. But also when talking about sort of tackling energy and emissions through energy, the environmental sustainability element, there are also other benefits that we can try and tackle and we need to address, which are energy security and energy equity and ensuring equal and affordable access to energy for everybody. So this is a slide from which takes a couple of diagrams from a really great report I'd encourage you to have a look at. It's called Zero Carbon Britain. It's published by the Centre for Alternative Technology. And they've done lots of work and modelling how we can get to a zero carbon Britain. And so here you can see on the left-hand side how we can reduce our emissions from the emissions in 2017, how we can reduce those, and significant reductions in transport, and also in buildings, heat and hot water as two major areas to create reductions in our carbon emissions. But then we also think about how we produce our energy. And so all of this grey stuff is our fossil fuels that we need to get rid of. They've also removed nuclear. And we can see here, a big increase in our renewables being needed. And we're also seeing that happen already. But we also see changes within our electricity network as we increase the amount of renewable energy, which is occurs at different times in different places and is less predictable. We need to develop our energy systems in different ways, and we need this. This is sort of referred to decentralization of energy, where we can produce it locally. But that requires us also digitization and the use of what we call smart energy networks to try and balance the supply of energy supply from renewables and our energy demand. And all of that will lead to decarbonisation. And so there's a huge shift within our energy systems. We see new products being produced on the market, new services around energy. We see new generation solutions. We see new storage solutions. You hear about electric vehicles, but also hydrogen being used as a way of storing energy. There's lots of really exciting new innovations within the energy sphere. And a lot of that is supported by what we call big data analytics, the use of artificial intelligence and machine learning in order to work with the sheer volumes of data that come from digitizing our energy systems. But of course, how much are the wider public aware of these changes that are happening? And what we see in terms of sort of changes happening, here we can see this is what has contributed, the different sources of energy contributing to the electricity grid from 2012 at the top down to 2020 at the bottom. And the one thing that I would ask you to focus on is this black here. And this is coal. And this shows us how we have, over just this past 8-year period, reduced the amount of coal in our electricity network right down. And so, we see lots of coal-fired power stations now being closed down in the UK. And linked to that, this diagram up on the right tells us about what we call the carbon intensity of our grid, which is how much carbon dioxide is embedded within each kilowatt hour of electricity produced. We can see that actually there's much less carbon dioxide produced for every every kilowatt hour produced. Now, again, I just want to quickly talk about Kiel. There's some really exciting things happening at Kiel. We have a new solar farm, a new 2 big wind turbines and battery storage, which will be in the next few months producing on our campus at Kiel. And what that has meant is that we have also invested significantly in what is called our Smart Energy Network Demonstrator. So this idea of trying to manage energy in a really digital way, digitized way, to help us balance all of the renewables that we're about to produce on site with our supply, to try and make sure that we make the absolute best use of that renewable electricity that we're producing to reduce our carbon emissions. And I'll say that the picture of David Attenborough is there because we announced our climate emergency on the day that David Attenborough came and visited Kiel and heard more about our sustainable energy projects. So, these just really sort of highlights that organisations actually are developing really exciting and innovative sort of new ways of managing energy and trying to reduce our carbon emissions. Energy, of course, also involves mobility or travel and transport. And this is, again, a finding from the Centre for Alternative Technology Zero Carbon Britain report. And this shows, differences between 2017 and a Zero Carbon Britain future, where we majorly reduce the amount of miles being driven by car, and we increase the miles being carried out by public transport, more by motorbike rather than car, more by cycling, bit more by walking. So we need to change our mobility and our transport and travel infrastructure. And that on the right, this is showing ways that reducing demand can decrease our emissions, as well as through improved efficiency as well. And of course, there's a lot to learn about sort of COVID. We've learned how to do things differently, requiring, different sort of travel patterns. And it'll be really interesting to see what changes in the long term, which can help us towards this net zero future. Okay, the final thing that I want to focus on in the last few minutes is thinking about what are called nature-based solutions. And so this is some extracts from a report from the House of Commons Library from the UK Parliament. And it talks about, what are nature-based solutions? So it falls into two categories. One is in terms of avoiding emissions from natural ecosystems. So ensuring that we manage sort of the activities of these ecosystems to reduce the release of greenhouse gas emissions. And also another category is what's called negative emissions, or sometimes you'll hear the phrase negative emission technologies, but actually that can mean trees, fantastic negative emission technologies, ways of removing carbon dioxide from the atmosphere and storing it, but storing it in soils and peats as well as the sort of plant biomass as well. What for me I think is really exciting is, as a geographer and an environmental scientist, there is a really clear role for the physical, for the environmental sort of side of our subject to play a really important role in these solutions, through really trying to understand the science behind how to make sure that our natural ecosystems best contribute to our zero carbon future. And so this is again from the Zero Carbon Britain report, and just sort of highlighting, the carbon which can be captured through our unharvested forests, as well as our harvested forests, but also our soils and also our peatlands. If we can undo some of the damage that we've done to environments such as peatlands, and learn to manage them better, and learn to manage them for carbon storage, as well as there are other things that we need these resources for. And so there's a really important role for geographers, for environmental scientists here to help us understand how to best do this. But of course, the other thing is it allows us to tackle the other emergency, the ecological emergency, the fact that we are seeing such negative impacts on our biodiversity. We see these things coming together now so that we can tackle climate problems while also tackling ecological problems as well. And so but my final sort of nod is just, other solutions. I've only talked about sort of energy systems, really briefly about nature-based solutions, but actually greenhouse gas emissions are produced in all parts of our life, all part of our society, all parts of our economy. And of course, there are many, many more solutions that we need to embrace. And so we are living through a really interesting time. It's really exciting times because of the shift that our whole systems need to make and are making to really sort of tackle this net zero challenge and target that we have. And so by way of conclusion, to try and draw out some of the key points of what I've been talking about very quickly to you for the past 50 minutes, is saying we need to understand the science because it helps us make the emergency clear. It also helps us educate other people as well as educating ourselves about what we can do. We need to understand systems, and understanding systems helps us understand the problem and the solutions. It helps us understand the bit of the system that we can shift to create the change that we need. Our solutions require a major change to our energy systems, where 75% of our emissions come from, which includes transport and industry and buildings. But it isn't just our energy systems. We need significant major change in our social and our economic systems as well. But solutions also require us to work with ecological systems. This, I think, is the thing that is so exciting, that we are bringing ecology back into the equation of thinking about solving big challenges. And we can solve the climate emergency and other problems at the same time. Tackling many issues within the energy system will also help us tackle issues of poor air quality, issues of poor housing, needs to be tackled with equity at its heart. And ultimately, my conclusion is we need geographers, because as geographers, we think in these systemic, joined up ways that cross between the physical and the human sphere. And climate change, the climate emergency, needs people who can cross between that physical, natural, and human systems. My final quote for you is this from the chair of the Climate Change Committee, saying, "The science demands it, the evidence is before you, we must start at once, there is no time to lose." And with that, I would just say thank you, with a beautiful picture of the Keele University campus. We've got a bit of time for questions now. Feel free to get in contact with me. I have an email address there. You can contact with me. You can find me on Twitter, and I look forward to carrying on that dialogue with you. Thank you very much.
Thanks a lot, Zoe. That was really, really interesting stuff, and really positive and uplifting at the end, I think, with the kind of the need for more geographers and more people to get involved in geography to solve some of these problems. I'm going to give people just a few seconds to ask any questions if there are any. And in the meantime, I'll just remind everybody of the things that I said at the start, which is that you can go back and you can watch this all in full on the GEO website. You can download the PowerPoint, and you can catch up with any of the events that we've had this term and last term, and you can catch all the upcoming events in the live events section of the GEO website. There's lots of stuff still to come over the next few weeks. I'm just looking, and I don't think there are any questions this week, so I think we'll leave it there. So thanks again, Zoe.
Super. Thank you, everybody.
Bye.
Bye.